Welcome back to this series of short videos on software-defined systems. I'm Claude Belil from Viavi Solutions. In the previous video, we concluded with the challenges and needs posed by the software development of heterogeneous embedded and distributed system, HEDS. We proposed to move away from proprietary software architectures that are too often project-specific and would lock you into specific hardware. We mentioned that software reuse instead of rewrite could be very beneficial to the speed up of the development cycle and lower the project cost. In this video, we will look at software architecture, or the underlying infrastructure that defines the complete life cycle of the software from how it is designed, loaded on the platform, connected, configured, started and stopped and removed. We will look at some open architectures and see how the SCA stands out for the development of HEDS. Now, the vital questions we must answer when developing software-defined systems. How to protect against system obsolescence. With the rapid obsolescence of hardware component and therefore the need to change the processors or peripherals, how can we minimize the impact on the costly developed software applications? How can we change hardware components without having to rewrite the software? How to draw the benefits of the HEDS environment, which is how to minimize the complexity of the software applications while still being able to use multiple processor types in a distributed approach to optimize the signal processing. How to develop more complex applications, but yet assure resilience. This relates to the above, but from a performance and testing capability. With the platform and software complexity ever increasing, how do we make sure that we don't create monsters with our software code and a change here would result in bugs somewhere else? How can we keep our software testing simple? How to reduce the development cycle to shorten the innovation cycles? Time to market is the key. It's about flexibility. Here is a quote that I particularly like and that is applicable to our case here. As with all the species that survives, we must design and develop our systems with the capability to evolve, to adapt to changes, to introduce innovations, without having to start again from a white sheet of paper. There is almost no point in designing something that is so rigid that any requirement for change will set you back months in your development cycle. Developing software application is somewhat similar to a construction project. Instead of using brick and mortars, we use software code. We assemble lines of code, each having specific roles, being controlling the ins and outs into the programs, directing the data to the appropriate rooms or routine for processing. You could build a house without a plan, but surprises are to be expected, often forcing us to redo things. And often these fixes will create other types of problems that were not there before. Similar to a house, we should be building according to a well-established plan to prevent any surprises that would force us to tear down walls and rewrite software because of conflicts. To meet those demands, we must start on a solid base. The software architecture orients the design decisions, foresee problems ahead of time to simplify the implementations and to avoid costly changes after the fact. The spaghetti code problem. It focuses on the structure rather than the implementation details. We must consider the constraint imposed by the requirements as discussed before, protect against hardware obsolescence, speed up innovations and lower development cost, and adapt to the ever more complex hardware platform. You could certainly sit down and create your own architecture. The literature is full of books providing information on how to create your own architecture for your projects. Over time, multiple architectures have been developed to address those challenges and facilitate the development of software for SDS. On the commercial side, one may name Microsoft.NET, or the Enterprise Java Beans, Corba Component Model, or the AUTOSAR. But as you see, while they have been great for their domains, they still have drawbacks when considering HEDS. Microsoft.NET requires x86 and Windows. Java is an interpretive language and is not really suitable for most real-time embedded systems. CCM, Corba Component Model, is mainly business-oriented, and AUTOSAR focuses on the automotive industry. On the military side, a number of standards have been developed in an attempt to standardize the development of software for heads to promote interoperability. For example, the GTNC APIs, Victory, Lavosar, Mora. Those are all sets of APIs for their different domains that can help abstract the software from the hardware platforms to facilitate software reuse and portability. But they're not really complete architectures. Looking at the complete architecture or the lifecycle infrastructure, we have a phase, which is heavily influenced by the DO 178 safety standard for aviations. The European component-oriented architecture and the software communication architecture are truly software architectures for the development of generic heads using domain-specific APIs as mentioned above. Focusing on the SCA, it is a standard that was initiated by the US Department of Defense for a major radio replacement program in the late 1990s. But rather than developing it for their own needs only, the US DoD opened the specifications to the international community under the umbrella of the Wireless Innovation Forum, asking industry, academia, and government labs to participate to improve the specification. The first publicly available specifications came out in the early 2000s, and multiple revisions have been published all the way to version 4.1, which is now the de facto standard since 2015. The SCA has now been adopted by multiple defense departments worldwide as a requirement for the development of future radio program. Hundreds of thousands of radios have been deployed based on the SCA. But what is really the SCA? It is an international open standard developed to promote application portability and software reuse across heterogeneous embedded and distributed systems. It is a methodology to develop software components for heterogeneous systems promoting software reuse and portability. It is a framework to deploy, interconnect, and control any third-party software components. It is platform agnostic, and it is also domain agnostic. It's all about software component, not about applications or domains. In the next video, we will dive into the technical aspects of the SCA. We'll show how it was designed to address the challenges exposed previously, how it promotes software reuse. So join me on the next video, the what of the SCA.